welcome to the course on molecules in motion. In the last class, we were talking about the various types of electrolyte, and we discussed about the strong electrolyte, and we had talked also about the weak electrolytes. But before we go into any further, I would like to briefly summarize what we had talked about in terms of the weak electrolytes. So, in the weak electrolytes, what we were talking about is how the molar conductivity is going to vary with the concentration, and here we were talking about starting from the beginning of the types of classification of types of electrolytes. We were talking of the variation of molar conductance with the under root of concentration, and this concentration term is in molarity. Okay. So, the variation which we are looking into, if we are having two types of electrolyte, like a strong electrolyte and a weak electrolyte, as you can see from the two graphs, this is to summarize how the variation is going to look like. This is for a strong electrolyte and this is for a weak electrolyte. For the weak electrolyte, the variation of the molar conductance with under root of C, that is the under root of molar concentration, the variation is very large. The variation is very large, so large that we cannot find out the limiting value or the value for molar conductance at infinite dilution, the lambda naught, through extrapolation. Like if you had a strong electrolyte, what we can do? We can extrapolate the value of the molar conductance to concentration equal to 0, and we can find out whenever it is intersecting the axis of the molar conductance, we can read them as the value of lambda naught, that is the molar conductance at infinite dilution. But when you see that, when you compare that graph with that of a weak electrolyte, you will see that you do not have an intercept as such. So, it is very difficult to get an extrapolated value for getting the value of the infinite dilution of molar conductance. And since molar conductance, as you know, we have discussed this previously, it is going to be dependent on what? It is going to be dependent on the number of ions which is present in the solution and the interaction between the ions. Okay. If we have that, we can see what are the parameters it is going to depend on. So, the molar conductance of a weak electrolyte, how is going to vary with the concentration, and concentration is under root of the molar concentration. The variation of molar conductance lambda m with dilution can be explained on the number of ions in solution. Okay. So, it is dependent on the number of ions and their interaction. So, how the variation of lambda naught or lambda for that matter for a electrolyte which is weak can be explained on the basis of the number of ions in solution. The number of ions furnished by an electrolyte in solution depends on the degree of dissociation, and this degree of dissociation is going to be the amount of ions which is going to be generated when the electrolyte is put into the solution. Okay. And what happens? The number of ions is going to increase if the dissociation is higher. So, if the degree of dissociation is large, then the number of ions we get in the solution will be larger. So, if we increase dilution, the degree of dissociation increases. So, if you increase dilution, the degree of dissociation increases, and hence the number of ions in solution becomes larger. As a result, the molar conductance increases for that electrolyte. But compared to that of a strong electrolyte, when we consider a weak electrolyte cannot be completely dissociated. We always have a term called as degree of dissociation. Degree of dissociation should be 1 if they are completely dissociated. So, it is you usually have a fractional value of degree of dissociation which is associated with a weak electrolyte. So, if it is a weak electrolyte, we do not have complete dissociation. So, it is not possible to apply the law of independent migration of ions. which is given as the Kohlrausch's law. Okay. What do you have if you have independent migration of ions? If you have a strong electrolyte, they are completely dissociated, then the total molar conductance of the solution can be is actually the sum of the molar conductance of the individual ions. Okay. But when we are talking about a weak electrolyte, we cannot directly apply the Kohlrausch's law of independent migration of ions. The molar conductance at infinite dilution of the weak cannot be determined through the just addition of the two ions of cation and anion. Okay. So, what we have to do? So, the degree of dissociation alpha of a electrolyte, which is defined as the ratio of the amount of ions formed in the solution to that of the amount of electrolyte added to the solution. Whatever you have added, how much is if you get the same amount, then they are completely dissociated. But if you get a number of ions formed is less than that of the total amount of electrolyte you have added, then you have a fractional value of that ratio, and that is given by the degree of dissociation. Since only a fraction of the electrolyte is actually present in the ion form, means they are dissociated. So, we can say the molar conductance should be that fraction multiplied by the molar conductance at infinite dilution, because we have the ratio of molar conductance at any concentration divided by this, the molar conductance at infinite dilution being equal to alpha. We have also seen that if you have Ostwald dilution law, which we had derived in the last class, is a method of how to find out the value of infinite dilution. At infinite dilution, what is going to be the molar conductance of a weak electrolyte can be found out from Ostwald dilution law. In Ostwald dilution law, what you have? You have the measurement of various measurement of molar conductance at various concentration. This we had derived for a weak electrolyte. We had taken example of a weak acid, and from this expression we can see that if you are plotting 1 by the molar conductance versus this parameter, then the intercept what you get is going to be 1 by molar conductance at infinite dilution. So, from that intercept we can find out the value of So, this is the thing which I am looking into. I have plotted this as the independent axis here, and the dependent axis is 1 by the molar conductance. This is the y axis. So, if I plot this, then the intercept which is at 0 concentration will give you the value of 1 by molar conductance at infinite dilution. So, if you through a experiment for a electrolyte at various concentration, if you are taking a weak electrolyte, you are measuring the molar conductance as at various concentration, using a conductometer. You use a conductometer to find out this concentration. The molar conductance can be measured for each concentration. For a known concentration, you keep reading the value of the molar conductance from the meter, and then you plot 1 by the molar conductance at various concentrations with the molar conductance value multiplied by the concentration. From this expression we can see this is if it is a straight line plot, this gives the intercept. So, I get the intercept if I extrapolate the value, I get the intercept, and this intercept is going to be 1 by the molar conductance at infinite dilution. So, I can find out what the value is, right. So, we can say that according to Kohlrausch's law, the conclusions that we have, that ions of all electrolytes begin to migrate independently as the solution is diluted. The ions in dilute solutions are so far apart that they do not almost have any intermolecular interactions. so they do not interact. Under these circumstances, what we can have? We can have the molar conductance at infinite dilution as the sum of the molar conductance of each of the cation and the anion at the dilute solution. So, this is how it is represented. So, based on this Kohlrausch's law, we can say that the molar conductance at infinite dilution of the cation and anion for a certain electron can be added or subtracted to get the molar conductance of a desired value of for a desired electrolyte. That means, the molar conductance at infinite dilution for a given electrolyte can be found out by combination of either addition or subtraction of various values of molar conductance of cations and anions, which is known to us. So, it may be noted that the lambda naught values for a weak electrolyte can be obtained through this indirect method. So, how do we do that? Here, this is the reason I have taken this example, is that we need to know where we can apply the Kohlrausch's law and what all we can determine using the Kohlrausch's law. If you are having a Kohlrausch's, if you want to use if you are dealing with a weak electrolyte and you are applying Kohlrausch's law, in the sense that it is indirectly applied, what can you find out? You can find out the molar concentration, calculate the molar concentration at infinite dilution for that weak electrolyte. You can calculate the degree of dissociation of that weak electrolyte. You can calculate the degree dissociation constant of that electrolyte. So, based on that, let us see how we can do each of them. So, first let us concentrate on calculating the molar conductance at infinite dilution of a weak electrolyte. Let us consider the classical example of acetic acid. So, the limiting conductance which we are interested to find out is for acetic acid. According to the Kohlrausch's law, what you have? The molar conductance at infinite dilution, which can be either represented by infinity sign or by a not sign, 0 sign, of acetic acid will be what? If I say they are completely they are supposed to be dissociated, they are dissociated into acetate ion and the H plus ion. Okay. So, we have the infinite dilution the value of the acetate ion plus the infinite dilution value of the H plus ion. Okay. So, this equation can be obtained by the knowledge of molar conductance at infinite dilution from some strong electrolyte. For example, let us consider HCl, NaCl and sodium acetate. These all are strong electrolytes, and if I see each of them how they dissociate and what are the parameters we can get from here. Suppose we take HCl. HCl, if I say it is a strong electrolyte, so we can apply Kohlrausch's law. All of them are strong electrolytes. So, for all these we can apply Kohlrausch's law. So, for sodium acetate, it dissociates into acetate ion into plus the sodium ion. So, here I can say the lambda value or the molar conductance at infinite dilution for a strong electrolyte like sodium acetate is going to be the summation of the lambda naught value of the acetate ion plus the lambda naught value of the sodium ion. Okay. And when we are talking about HCl, it is again a strong electrolyte, it is going to be completely dissociated, and all the solutions which we are talking about right now is in water. So, if we are having HCl in water, it is going to be completely dissociated. What will you have? The molar conductance at infinite dilution for HCl will be nothing but the molar conductance at infinite dilution for the H plus ion plus the molar conductance at infinite dilution of the Cl minus. Similarly, you have NaCl. Now, what we are interested? We are interested in finding out the molar conductance of at the infinite dilution for acetic acid, for which these are the two parameters we need to know, the molar conductance at infinite dilution for the acetate ion and for the H plus ion. So, how can that be represented? We have this to be represented in the form as here you just see what can you information you have. You have for the acetate ion, you have for the sodium ion. You do not need the sodium. You have the H plus ion, you have the Cl minus. You do not need the Cl minus, and you do not need the Na plus ion either. So, you need these two ions, and how can you get for these two ions? you see what you have done, you have taken the sodium acetate, that means these two ion, plus you have added HCl, this two ion, and subtracted NaCl. So, what happens if you have added these two, and from this you can see that the values for Na plus can be eliminated, for the Cl minus can be eliminated. So, what you are left with, the lambda naught value for the acetate ion and the lambda naught value of the H plus ion. So, this is how you do it. Similarly, that means what we have come down to, the acetic acid, the molar conductance of acetic acid at infinite dilution will be nothing but the molar conductance of sodium acetate plus the lambda value of at infinite dilution for the HCl minus that of the molar conductance value at infinite dilution for NaCl. Similarly, you can find out another example is the ammonium hydroxide. Ammonium hydroxide is a weak electrolytes. For that, we can find out the values at infinite dilution by adding the strong electrolyte lambda naught value for the strong electrolyte like ammonium chloride plus the sodium hydroxide and subtract sodium chloride. So, then you are left with this ion, ammonium ion plus the OH minus ion. So, this way you can find out the value of the infinite dilution. You can calculate the degree of dissociation for a weak electrolyte, and the degree of dissociation is nothing but the molar conductance of at any particular concentration divided by the molar concentration at infinite dilution. Thus, by measuring the molar conductance at any concentration C, we can find out the lambda naught lambda m value at any concentration C. One can calculate the molar conductance at infinite dilution if the degree of dissociation is known, right. Now, dissociation constant of a weak electrolyte, this is what we had taken. Suppose we have a weak electrolyte like Ha, this is going to dissociate into H plus plus A minus, and if alpha is the degree of dissociation, then 1 minus alpha, that is initially it was 1, now the degree dissociation has started. So, I have subtract that whatever fraction which is getting dissociated into whatever fraction gets dissociated from 1 is the one fraction which is going to be generated. So, these fractions are going to be equally generated because it is a equation where you have the stoichiometry as 1. So, alpha C and alpha C will be the concentration after they have dissociated. So, the degree of dissociation for us electrolyte at any concentration for weak electrolytes like acid like Ha can be represented something like this, and from here if you know the knowledge of alpha, you can find out the constant value of the dissociation constant. Am I clear? Now, moving to a example as such, you see if you want to find out the molar conductance of acetic acid or ethyl acetic acid or any other higher acid, what you have the molar conductance of sodium chloride, HCl and the acetate ion, and these values are given to you. So, how will you find out? You know this is going to be the acetate and this is going to be the acid and this is going to be the sodium chloride. So, this is the way you add these values and subtract sodium chloride, you should be able to generate the value at infinite dilution. Now, let us move to another example where you have to be calculating the degree of dissociation and the dissociation constant of say 0.1 molar acetic acid, and given the specific conductance of the acetic acid is say 1.65 into 10 power minus 4 Siemens centimeter inverse, and the molar conductance at infinite dilution of, that means lambda naught for the acetic acid is given to be 390.6 Siemens centimeter square meter inverse. Okay. So, what we want to find out? We want to find out the degree of dissociation and the dissociation constant. Okay. So, dissociation constant for an acid is nothing but Ka equal to alpha square C divided by 1 by alpha. Okay. But if I want to find out this, what I need to know? I need to know the value of alpha. And for alpha, what I need to know? I need to know the molar conductance value at infinite dilution of that particular electrolyte and the molar conductance for any particular concentration. So, the molar conductance at a particular concentration can be given. What is given to us? Let us say we have to find out alpha. For that, we have to find out the lambda C value. The lambda C value or value, sorry, this should be lambda, no, this is not lambda naught, this is lambda C. So, the lambda C value is lambda specific conductance into 1000 by the molarity as per the definition of molar conductance. Please make a correction. I am going to correct it. This is not lambda naught, this is lambda C, that is the molar concentration, molar conductance at any given concentration, and that is nothing but the specific conductance at that particular concentration into 1000 divided by the molarity, right. So, if we look into this, what is given to us? Given to us is a specific conductance value of 1.65 10 to the power minus 4, and that should be multiplied by 1000 divided by the molarity. So, you have 1000 divided by the molarity. Molarity of the solution is given to be 0.1 molar acetic acid. So, it is 0.101 molar, the M is the unit molar concentration. So, this way you find out the molar conductance of this acetic acid at a given concentration of 0.01 mole, right. So, once you find out that, now you can use that value to find out the alpha, the degree of dissociation. So, the degree of dissociation is the molar conductance at a given concentration divided by the molar concentration at infinite dilution, and the infinite dilution value is given to you. The molar conductance at infinite dilution is given to us is 390.6 Siemens centimeter square into meter inverse. So, if this value is known and this value is known, this value we have calculated is the molar conductance at a given concentration 0.01. So, the ratio of this by this should give you the alpha. So, that is what we have done. We have calculated what the molar conductance value is going to be from the given value of specific conductance of 0.01 molar acetic acid, and that value we have divided by the lambda naught value of acetic acid, which is also given to us, and the ratio of that gives us the value of a degree of dissociation, and this degree of dissociation is applied into the expression for the calculating the dissociation constant of the acid. Dissociation constant, if the acid is supposed to be dissociating into HA equal to H plus into plus HA minus, then we have a expression like this: C into alpha square divided by 1 minus alpha. Alpha is known to us, so we can find out the degree of dissociation. Okay. So, this is what we have done with the conductivities of a weak electrolyte. Now, the next one which should be of interest is we have learnt about the strong electrolyte, we have learnt about the weak electrolyte, we have learnt how the different types of electrolytes are going to give rise to various dependence on concentration of the molar conductance values. But when we are talking about the transport properties as such, we are talking about the transport of charge. So, we have talked about in terms of conductivities. Now, how these conductivities are related to the movement of the charge, that is going to be a topic which we are going to take up the next. Okay. So, this is how we are going to look into in the next class. Thank you.